get started today. There is a sign-in sheet going around somewhere. Make sure you put your name, you write your name on it. You don't need to sign, you don't need to enter your cell phone number, just your name. This is, for my purposes, I have trouble associating names with faces, but at least I'll know the names here, right? It's a question of faces. We'll do that later. The second thing is about videos. For this class, Andrew has been kind enough to take these videos, and we posted the initial videos. We are on a little bit of a hiatus because we have to get approval from people. It turns out that some of what you say, your questions, your back of your heads are showing up in the video, so we have to, I want to cover my bases. Yes, that's fine. And in any case, likely they'll be up in a few days, that's my guess. That's the story. They'll probably not be on YouTube, they'll be on Stellar, but you guys can access Stellar, so okay. Questions? Anything? Good? Okay, let's get started. So, pseudo-random functions is what we're going to do today. The point is this, right? So we're going to start by going back all the way to the first lecture. And we're going to say, look, let's go back to Shannon. Okay? So we started with sort of Shannon's one-time pad and Shannon's lower bound. That says if you want to encrypt a message of a certain size, you need a key of size at least that many bits. Yeah, that's onerous. It's not going to work in the real world. In some sense, I mean, whether we said it or not explicitly, this whole effort has been to overcome Shannon's bound. This whole reason why we went to computational adversaries, the whole thing has been to overcome Shannon's bound, and we will do it in today's class. Using pseudo-random generators to begin with, to an extent, but really using a new notion called pseudo-random functions. Okay? So that's the plan today. All right. So let's see. So we saw pseudo-random generators. You guys remember what it is? Can anyone define it for me? What is the pseudo-random generator? Warmed up. First of all, it's a function. And so it's a function. I'll call it G. Name word, name character association. Yes. It takes n bits and maps it to something bigger than n bits. I want to expand. It's why it's generate, expand. And what is a security property that you want the pseudo-random generator to satisfy? Who is going to help me out? Yes. Oh.
Given the first I bits, you can predict the I plus first bit.
Good. So we saw this next bit unpredictability definition that says that for any I, an adversary that looks at the first I bits of the output cannot predict the I plus 1 bit. What does it mean? Cannot predict? Cannot do any better than a half. Coin toss in predicting. It doesn't have to predict it completely correctly. It just has to do it 51%. Okay? That he can. Even that he cannot. Then we saw other definitions, right? One other definition, actually, to be honest, right? So what was that? Remember? Do you want to give it a go?
Yeah, the next bit, unpredictability.
Which is what he said.
There's also the indistinguishability.
Indistinguishability definition, which says
you cannot. You have an algorithm and you decide between the pseudo-random string and the actual random string.
Random string. So we call this the Turing test in a sense, right? I mean, no probabilistic polynomial time algorithm can distinguish between two experiments. One, it's given a truly random m bit string. M is large. Two, he's given the output of the generator from a random m bit string. These are very far distributions, statistically extremely far distributions. He cannot distinguish. That's what it is. Okay, so that's very good. So let's now get going and let's see how to construct an encryption scheme. A secret key encryption scheme. Not quite that ambitious yet. Okay, so how do we construct a secret key encryption scheme? Because here is a candidate. Jen, I want Jen, yes. It outputs it samples secret key. This is what it has to come up with. It is number S, which is randomly chosen, this means randomly chosen, from the set of k bit strings. K is a security parameter. Now I'm going to assume that there is a generator, G, that expands k bits to, let's say, m bits, m bigger than k. And m is not very much. L is bigger than k. Thank you. Sign up sheet here. You don't have to do it now, but and all right. So what's my goal? I have a key of length k, and I want to encrypt a message of length bigger than k. Okay, I want to encrypt a message of length L, let's say. How do I do it? Okay, Shannon said, take the secret key, exclusive OR with the message. Okay, so that's what he said. Encrypt secret key and the message. What do I do now? That's not going to work. Because I don't know, the secret key is k bits, the message is bigger than k bits. It's not going to work. So what do you do? True, but how? Like, one-time pad is such a beautiful idea that I'm never going to let it go. I'm going to hold on to it, like my dear friend, throughout the class. Okay, that's a hint for you. What do you do?
Yeah, so you can XOR like G of S with the message.
Correct, right? So I want something to XOR with the message. Okay, one-time pad, yes? What do I XOR? S, no good, because it has fewer bits. I pad S with a bunch of zeros, no good, because I'm revealing the last few bits of the message. So what do? I take S, I expand it into a string that looks random for all practical purposes, against all polynomials and adversary. And my ciphertext, C, is G of S, exclusive of the message. So this actually, one can prove that if I give you an encryption of message 0 or message 1. You pick message 0 or message 1. I'm going to encrypt one of the two. You can't tell what is what. Yes, in fact, you can't tell if I give you a random string or a real encryption of one of the two. So this is something we can prove, and in fact, we'll prove it in the next class. I'm not going to do it formally today. But this is a candidate. How do you decrypt again? I mean, security is one thing. Correctness is get another. So decryption gets a secret key. So it's a symmetric key or secret key encryption scheme and the ciphertext. What does the decryption do? It's too obvious? It doesn't matter. Just spit out.
It XORs GFS with the ciphertext.
It exhausts GFS with the ciphertext. Yes, and the beautiful property of exhaust says you're going to get the right one. Okay, that's very good. What did we do? We encrypted messages that are longer than the keys. Shannon said this could not this could not be done if you wanted information theoretic security, unconditional security. You're not getting it. You're only getting security against polynomial time adversaries. That's the whole cryptography. You can do much more if you relax your conditions, from the unconditional. All right. So this is a very good encryption scheme. Well, not very good. It's a good encryption scheme, but not very good. Okay. Why is it not very good? He knows the pseudo-random generator. He knows the function. Yes. The only thing he doesn't know is a key. So what does he see? What does the adversary see? He sees G of S exclusive OR with the message. Pseudo-randomness says that you cannot distinguish between the case when I pluck out G of S and put a random L-bit string in its place. You cannot tell apart. But if I put a random L-bit string in its place, the whole thing is random. Yes? A random string XOR with the message is truly random. It destroys all information about the message. That's like a one-time call. And so you cannot tell. That's why it's secure. We will prove it in the next class, but yeah.
But if you put a real random generator there, and the probability that the adversary correctly guess the key is like 1 over 2
to the k.
To
the k, right? Good. Excellent. So we are going to have to relax Shannon's perfect security condition. The adversary is going to be able to break this with probability 1/2 to the k, yes? But that's okay. So we are going to take a deep breath, relax, okay? We are going to set k to be 256. So then he's 1 in 2 to the 256 is the probability. What is 2 to the 256? It's bigger than the number of atoms in the universe. There is no way in hell he's going to. Yes. You have. So this is along the lines of what we call approximate security in the problem set. Yes, I mean that was a problem in the. We're going to relax it a bit, but that's good enough. That's good enough. And you have to relax it. Otherwise, there's no hope. Otherwise, Shannon comes back and says, no. Right. All right. So this is a decent scheme. Not embarrassing, but not great. Yes.
What if your output is longer than the fixed output of the generator?
What do you mean? What do you, your output? The message.
Yeah. What if your message?
Ah.
Yeah.
Okay. Good question. What do you do? Not clear, right? Or even worse, actually. I mean, who says I'm going to encrypt? Who says I'm going to get all the messages I'm going to encrypt in my lifetime in one shot? It's not just a problem that the message is longer than the output length of generator. I may not even know how long a message I want to encrypt through my lifetime. Okay? I don't know. I mean, do you know how many emails you're going to get? I don't know. This is a continuous process. Yeah? So, how do you do that? Okay. So, good. Yeah. So how do you do? Well, you need to have something a little stronger than a G that expands from k bits to a fixed L bits. Okay? Well, we saw this in the last class. If you can expand from k to even k plus 1 bits, I can expand from k bits to really any polynomial number bits. So I can dealing with messages longer than L or many messages. That's what I'm just going to call it. But shorthand is the messages keep coming. Right. How do I do it? I take a pseudorandom generator that not just stretches to L bits, but it stretches to any polynomial number of bits. So I'm gonna say, this is my shorthand, right? It doesn't say it just outputs up to a number of bits, but I can keep generating as many bits as I want. I can keep extending this one. This we know how to do, right? I mean, remember how would you do this this sort of thing? Here is one way. Take a seed, yes. You ask me for, I mean, there are many ways of doing it. So you ask me for the first block, yes? I'm going to run this nice generator. Let's say for a moment that L is actually 2K. Okay, that's what I have at hand. This I can build. Even one bit extension, I can make it into a K-bit extension. This I can do. And let's say I have. How do I extend it to arbitrary number of bits? I take S, I apply the generator, so call it G of S. I am going to denote, this I'm going to use throughout the class. Okay, so G of S is what? It's a 2K bit string. S is K bit, G of S is 2K. So I'm going to call it G0 of S, comma G1 of S. What does that mean? First K bits, the last K bit. That's it. So when I apply a G to S, I get a 2K bit string. what am I going to do with this 2k bit string? The first k bits, I am going to keep it for myself. Now I'm going to the last k bits I'm going to output. So this is the output. Okay. The first k bits, what am I going to do? I'll keep it for myself. The next time you ask me for another block of k bits, I'm not going to use s. S gone, right? I mean, what can I do with s? I can apply g. I've already applied g and got everything out of it. I'm going to apply g on top of g0 of s. And I'm going to get what? G0 of G0 of S and G1 of G0 of S. Those are the two halves. And I'm going to output G1 of G0 of S. I'm going to keep G0 of G0 of S for myself. Yes?
What if G0 of S is in some way similar to S? Like, you might not.
What do you mean similar to S? Can it be S? Let me ask you a question.
Like, S is random, so like, if you just output S, that would be like a valid generator, right?
No, but it won't expand.
Well, fine, but like...
What you want is the following, right? When I'm in this situation, right, when I use G0 of S as the seed for the next iteration, what I want is that G0 of S is random, conditioned on what I already gave you, which is a function of S. Pseudo-random generator guarantees this. Pseudo-random generator guarantees that the joint distribution of G0 of S and G1 of S is truly random. In other words, conditioned on the first half, the second half looks right. Conditioned on the second half, the first half looks right. Conditioned on any subset of bits, the other subset looks right. So that's the key. It's very important. So think about a generator. Think about a situation where G0 of S is S itself.
Yeah.
That would be bad, right? But that won't be a generator, right? If this is S, the second half is not unpredictable given the first. It's not a generator by definition.
Okay.
Very good question. This class is called Cryptography and Cryptanalysis for a reason. I do cryptography, you try to do cryptanalysis, okay?
What if your message M is like less than L? Do you pad it with like
Pad
zeros?
with zeros, yes.
So if you pad it with zeros, then you can get the last few bits
No,
of
you
GFS.
cannot. You cannot. You can. If I pad the key, if I pad the one-time pad, if I put zeros in the one-time pad, then I can get the last few bits of the message. If I look, I mean, for any two messages, right, the ciphertext of one message and the ciphertext of the other message look indistinguishable. It doesn't matter what the two messages are. They could be 0, 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, whatever you want. You come up with it.
But if like message is like 1 bit long and you had like zeros with the rest
Yes.
of it, then you get the last.
No, you don't.
Um,
No, you don't. Who gets it?
well, the ciphertext would then be like G of S. The last like n-1 bits would be G of S.
Yes, so what?
So then can you use it to like generate? Oh, but that's like.
No, you look at it. You look at the ciphertext, okay? It's G of S, exclusive OR, with some string.
Mhm.
I'm telling you that G of S, right? G of S, by itself, if you look at it, it looks completely random. So it looks like a completely random string, exclusive OR with a message. In this scheme. Here, you need an argument to show that this is actually a good thing to do. And intuitively, the argument is my reply to Marguerite's question, which is that, the new state, so imagine a game where I forgot everything about it. This guy I started afresh, okay, new S prime. That's the effect I want, and pseudo-randomness, the definition guarantees that is. Namely that even if I give you G1 of S, the last half of the bits of S, of G of S, you won't be able to tell what G0 of S is. In fact, it's indistinguishable from random for you. So as good as trash. Then I continue. Keep using it. Yes, so this I can do. This I can do. One needs a proof. One needs a proof. Okay. I have two words for you. The proof for the proof. Okay. Which is what we saw in the last class. There is a proof for this, and I recommend you go back and hammer it out. Hybrid argument is the two magic words. Okay. One can show that the sequence of outputs of this generator is indistinguishable from a truly random string of and this goes along. So this is, so again, this is internal secret state. Never output. These are the. So this is how I expand. So now you tell me, encrypt a message, okay? So let's say for a moment that my messages are all sort of L-bit strings, so, or rather K-bit strings, okay? So if they're not, chunk it up, right? So the first K bits, I take this guy and exclusive OR with the message. The second K bits, and so on and so forth. Okay? So this is what my ciphertext looks like. Yeah. Good. Okay. So that addresses your concern. How do you encrypt long messages? And this, if you go to other parts of cryptography, it's also called a stream cipher, which for a good reason, right? Also called a stream cipher. Still, I'm not happy with it. Still not happy with it. Why? Yes.
Like, if the other person wants to decrypt,
Yes. Good. What does he have to do? He has to know which message in the sequence it is. Yes? I encrypt the ith message using the ith block of this process. Yes? The decryptor knows the CS, the adversary doesn't. Right? The decryptor knows the CS, so he can recreate the entire process. Yeah? So he has to know which message I'm transferring. And the sender has to keep state, right? The sender has to remember, has to keep a counter that says, every time I encrypt something, I augment it. And I send this counter along with the message itself, so the other guy knows. But either the receiver has to be synchronized with the sender, or the sender has to keep this counter, which cannot be reset. I mean, if for some reason he loses state and loses this counter, you know which scenario you're back in? It's a one-time path scenario, because you're going to go back and you're going to re-encrypt a new message with the same seed, and you don't want to do that. So that I don't want. I want a completely, so this gives you a stateful encryption scheme. Stateful, why? Because stateful, I have to keep a counter, that's it. I want a completely stateless encryption scheme. Yes?
Does it matter the counter is followed?
It doesn't matter if the counter is followed. Yeah, it doesn't matter. The adversary can know, which. This is for passive adversaries. So we'll get to the active adversary case very soon in the next class, and then things change dramatically. But so far. Okay, so I want to be completely stateless. Yes, and the question is, I don't want to keep counters. When I get a message, all I have is a secret key. Yes, which I can put in a sort of a non-writable memory, a readable memory, read-only memory. I read it, I encrypt it. Don't keep any state. The next time a message comes in, do it again with no memory of what you did before. That's what I want. The question is, can you do it? Is it even possible? Yeah. Turns out the answer is yes, and we have to introduce a new notion called pseudo-random functions. Pseudo-random functions. It's a notion defined by what the Goldreich, Sharkey, and Silvio back in the 80s. And here's what it is. Okay. So let's imagine an experiment where instead of storing the S alone, right, I kept doing this process again and again and again and again. How many times? 2 to the n times. Something very large exponential number of times. I did all these things. And then I stored the outputs. I took G1 of S, the things in the below. I stored it and put it in my smart contract. Okay, that's what I did. And now I claim I don't need to keep state. Yeah? Why don't I need to keep state? Well, when I get a new encryption, what do? I say, I'm going to look up a random location in memory, right, and use that as a one-time number. Yeah? So here's the straw man solution. Of course, not a solution by any means. Right? So I store a very long G1 of S, G1 of G0 of S, G1 of G0 of G0 of S, etc. 2 to the n of the outputs. Something like that. Very large exponential number. So when I encrypt secret key and a message, well, by the way, this is not the secret key, this is the whole thing. Inside the stories. What do? I take a random R in 0, 1 to the n, right? Namely a random location in this array. And I say, well, I'm going to give you, so let me give it a name, okay? So let me give it a name, y1, y2, etc. In that case, I'm going to pick a random R from 2 to the n location, yeah. And I'm going to say, I will give you y sub r XOR with n together with r. So I tell you where I'm looking, pull out that location, exclusive R with the message, and give it to you. Okay. You can decrypt, yes? You don't need to keep, I don't need to keep state. Where is the state here? There is no state. Every time I'm looking at random ones. You can decrypt too, because you can recreate this whole big giant array. You know R, go look up YR, XOR with the message, you could. You should use the same thing again. Excellent. 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 Let's say I use this process to encrypt Q messages. Okay, Q messages. Q is polynomial. Of course, I'm polynomial time, you're polynomial time. Q messages. What is the chance that I will use the same location twice? Not Q by 2 to the n. Not Q by 2 to the n. You have to be very, very careful. Not Q by 2 to the n. So what is the process? I pick Q random numbers. What is the chance that some two are equal? This has a name. Believe it. Sorry? No. No. Yes. It's the birthday problem. The right answer is Q squared over 2 to the n. Pick any two locations. What is the probability that those two guys are equal? It's 1 and 2 to the n. How many pairs of locations are there? Q squared. Q squared over 2. Yes. But guess what? Q is polynomial, Q squared is polynomial. And 2 to the n is exponential. So it'll never happen. That's the beauty. If I store the polynomial length table, I'll be in trouble. As soon as I get to square root of that polynomial number, right? But that's not going to happen. Okay, so that sounds very good. Not very good. Good. Okay. Why not very good? Because I'm storing this ginormous table. Okay. If I were to store this ginormous table, I might as well store a random. Why did I go through this whole process? I might as well create an array of random bits and store it. Why did I do this to random generator? I didn't need to. Yes. So the whole question is really how to store a little bit and still make this process good. And that's what pseudo-random functions do. So let's see. So what are pseudo-random functions? Is a collection of functions in reality, it's a collection of functions. Okay. The nth collection will be a set of functions, fs. So this thing for a set of functions, this is for a particular function. So each function will be indexed by a string s, in 0, 1 to the k. And it will map some n bits to some L bits. Okay, that's what we'll do. It has two properties. Given a seed S is called the seed. It's a small guy that generates large guys. The seed in 0, 1 to the k, and an x in 0, 1 to the k. M, x is what I call R there. You can compute f sub s of x in poly time. Poly what? Poly k, poly n. Poly k. Poly k. Okay, that's number one. So if you look at the truth table of this function f sub s, that's like here. This is sort of like the truth table of this function. But if this is the truth table of the function, yes, can I satisfy that condition? So you know, f sub s could be the following function. Okay, f sub s on 1 is this. F sub s on 2 is this. F s on 3 is this. So on and so on. Would it satisfy that definition? Not really. Why? Yeah.
For one, it's like it already has to store like a non-polynomial number of bits. So like to go through it.
To what? So how would you compute? How would you compute f of 2 to the 50? Okay. I don't know. This process tells you go through 1, 2, 3, 4. You take 2 to the 50 steps. In other words, you take x steps to compute f s of x. That's no good. You want to take log of x. In other words, you want to take about n steps to compute this guy. This is not going to cut it. The efficiency definition. Okay. What does that mean? Turing test. That's how we will formulate security. What does Turing test mean? Imagine that there is a distinguisher, right? So I want to say these functions, if I pick a random function from this family, right? How many such functions are there, by the way? Just curious. Good, okay, so let's see. So how many functions are there from n bits to l bits? Right, so it's a class of functions. Yes? How many functions are there? Well, the first guy, there are 2 to the l possibilities. The second guy, well, there are 2 to the l possibilities. Blah, 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 blah. Okay, so it's 2 to the, let me give it a name. Collection of all functions from 0, 1 to the n to 0, 1 to the l, whereas this is sort of enumerate over all s in 0, 1 to the k. So there are 2 to the k functions here. Like how many ever seeds? Each function is indexed by a seed, so there are 2 to the k functions. How many functions are there in total from n bits to l bits? There are 2 to the L to the 2 to the n functions. Yes. There are 2 to the L possibilities for each output. Functions in total. Yes. This is an enormously large number compared to that. Yes. This is a doubly exponential number, 2 to the 2 to the n, more or less what it is. That guy is 2 to the n, 2 to the poly, which is much smaller, yes? And necessarily so. I mean, that guy is a, yeah? And yet, the security definition of pseudo-random functions says that if you give an algorithm access to a random function from that family, he wouldn't be able to tell between that and giving it access to a truly random function that is from this family. You can't tell. You just cannot. That's what I want. Yeah? So I'm going to write it down mathematically in the following way. I'm going to give the distinguisher oracle access to a function fs. Yes? So this is s is drawn from 0, 1 to the k. Oracle access. 1 to the k, why? Because I want him to run a polynomial at k time, a polynomial input line. So that's a trope, right? So what does this mean, this notation, d to the power fs? It means that the distinguisher d can use this function fs as an oracle, which means that he can make queries to this function. He can say, here's an x, give me fs of x. Here is another x, give me fs of that x. Keep going. And because he is polynomial time, which I didn't write down, for every probabilistic polynomial time d, he can only make polynomial number of queries. Yes. With every query takes a unit time. Yes.
Polynomial in K and or L.
Polynomial in K is what I would say, but you should really think about K and N as being polynomial related. So the security parameter here is how large the C is, which is K. And that's what I put. PPT here, very good question. Very good question. Quality of time. Yeah. So this is an experiment, right? And he says, I'll keep interacting with this guy. In fact, then don't have to ask all the questions all at once. I could ask a question, get the answer, and then I think for a bit, ask a question, get the answer, think for a bit, think once. In particular, my ith question can depend on the answers to the first I minus 1 questions. I can do some post-processing. Eventually, I say, that's it, I'm done. I'm going to output 0 or 1. 1 is my guess that I am in actually the pseudo-random world. I want to say this is about the same as if I it's negligible. So let's decode this. This is really absolutely the key thing you should remember. Okay. On the left is an experiment where the adversary interacts with a pseudo-random function, a random function chosen in the collection of this guy. On the right is he interacts with a totally random function. The f is chosen completely randomly from this collection. What is this collection? This is, by the way, all the functions from n bits to l bits. So if you pick a random function from the collection, it's a truly random function. Okay. So I interact with either one or the other, and I have to tell which world am I in. That's my, that's like a Turing test. But it's an interactive Turing test. Right? And the security definition says that no adversary should be able to win in this. Does that make sense? It's different from a pseudo-random generator definition, which was a one-shot definition, right? The test, the distinguisher got either one thing or another thing, and it has to say, here you can adaptively query. That's what the definition is. And what's beautiful is a theorem which we will prove today. Again, go back to a certain colleague. Well, more or less. If one-way functions exist, then so do pseudo-random functions. Yes? You can start from something extraordinarily elementary, like a one-way function. is the kernel of computational hardness, right? And you can build this extremely powerful looking object. So we're going to do it. We're going to do it. So really, if you think about it, the main sort of condition between 1 and 2 that this construction did not satisfy is 1. Efficiency was actually a huge problem. And that's because if I had to compute the X output, say 1, 2, 3, 4, then I have to go to. This is the problem we want to solve. So how do you solve it? People who haven't seen it before, probably. So look at that. Did I erase it? I did. Too bad. Okay. If I look at that computation, really, what is going on? Right? There is a notion of an internal state. Right? I output something. This is output. This is internal state. Then I update my internal state. And then I output something, and then I update my internal state. I output something, then I update my internal state. Keep going. Think of it as a graph. Okay, it's a graph. And it's a horrible graph. It's a line. You know, if you think about the diameter of it, right? I mean, it's a horrible graph. In this context. There are better things you can do. Right? So this graph has a property that if you want to get to the ith node, you need to walk I steps. What is a graph where if you want to get to the ith node, you number the node some way, you take essentially log I steps. A tree is a beautiful object, yes? That's what we want. Tree makes life many contexts. You go from exponential to linear, basically. All right, so tree is a good idea, but what tree? How do you do it? Then how do you prove security? That's yet a different story. Okay, so here's the construction. What do I do? Doing all sorts of suboptimal things, but that's okay. This is the GGM construction. Surround functions. Okay, so let me draw a tree. Tree. So what? What do I do with it? Look, I have two things, okay? I have an input and I have a seed. So far so good, right? The input I have no control over in some sense. I mean, the adversary is going to ask me for this input, that input, who knows? But the seed I know is random. That's how I pick it. So let's elevate it to the status of the root. Very good. So now what do I do? What can I, well, okay, I didn't say, what do you have at hand? You have a pseudo-random generator that maps k bits to 2 k bits, length doubling pseudo-random generator. That's what you have at hand. What do you do with this? There isn't very much you can do. Yes?
You throw that to one side.
Beautiful. G0 of S, yes, and this is G1 of S. Put that in there. Label the node, the left node with G0 of S, label the right node with G1 of S. So far I haven't said what you output, right? But I'm not going to say it until the end. I'm just going to label the tree. So what do you do with this? Now I'm playing with you, right? Okay, all right. Okay, this is G0 of G0 of S. And this is G1 of G0 of S. The right node is always sort of G1 of something, the parent, and the left node is G0 of the parent. And that's how you label this. Okay? So if it's this is the Xth node, is G sub, tell me what it is. X is what? So I'm going to label this is X1. The first level is labeled by X1, the second level by X2, X3, and so forth. So what is this, the label of the Xth node? X1, X2, X3, up to Xnth node. Could be one of them. Sorry?
G1 X1 of G0.
Good. So let's be more explicit. Okay. So this is the 0, 1, 1th node. Yes. So this is G1 of G1 of G0 of S. Yes. Oh, okay. Yeah, that's so good. So the Xth node, Xth leaf, really, if you leaf, if you number the leaves this way, is Gxn of Gxn minus 1 of Gxn minus 2, so forth. Yes, yeah. Now let's define the function. Okay. So fs of x, yes. So let me give this a shorthand. Let me call this gx of s. X is actually an n-bit string. Gx of s means this iterative application. Yeah, that's fx of s is gx of s. This is our construction. That's it. Yes. So really, if you look at the leaves, I have a collection of evaluations of the pseudo-random generator, but it's computed in this sort of much nicer way. Right? I'm being, there is this, is it the Stanford experiment? This marshmallow experiment, yes? So you say, they did this experiment with kids where they say, I give you a marshmallow and I measure whether you're going to immediately consume it or you're going to kind of hold on. Yes? So that construction is sort of like a kid who immediately consumes the marshmallow. Yes, I mean, like I generate 2 pieces of a pseudo-random generator. I use the one. I just use it immediately. Output it. That's it. End of story. Okay. That guy, he deliberates. Okay. He says, "Let me expand. Don't output anything yet. Let me expand. Don't output it." See what I'm saying? That's the good thing to do. Yeah.
But like in that construction, you can kind of like, I don't know if infinitely is the right word, but you can continually like create new pseudo-random numbers. But with this construction, like, can you use the leaf to keep on constructing, or you can't?
You can. But that's not the way to think about it in essence, right? So there, if I wanted the ith block, right, ith block of the pseudo-random block, I have to compute I times. Here, if I want to get to the ith leaf, what do? I compute this. I go down to the ith path. In how many steps? In log I steps. Log n steps. Log to the n steps. Okay? So, yeah. So you're doing strictly better here compared to it. So the reason you have to keep expanding this is because you only had polynomial number of blocks. You wanted a bigger polynomial number of blocks. Here you have an exponential number of blocks, leaves. That's it. End of story. Right? If you want one, you go down to the right leaf and pluck it out. That's what the construction is. Now you want to put security. Yes?
Isn't that assuming that L is equal to K?
What is L?
L
is equal to K.
space.
Yes, absolutely. This is assuming that L equals K. If you want L to be smaller than K, just cut off the few bits. If you want L to be larger than K, apply a pseudo-random generator to what you get done. Right? So you can do it. But so far, okay, good. So very good. So this is a function from n bits. N is the depth of the tree, so I can make it whatever I want. 2 k bits. Yeah? That's what it is right now. But you can shrink, expand. all this. Okay? Is that good? That construction is more or less clear? Hopefully more than less. Yeah, good. Now the question is, how do you prove security? Yes? All right. All right. Good. This I'm going to do by picture. I'm going to erase this. Yeah. Before I do this, I need a little lemma. Here's a little lemma. Lemma about what? Lemma about pseudo-random generators. Okay. So let G be a PRG. I want that for every PPT algorithm D, for every polynomial P, P is a polynomial on what? On K, let's say. P equals P of K. And G expands from K bits to bigger than K bits. The following two experiments are indistinguishable. So I give the distinguisher, well, first of all, I pick S1 up to SP randomly from 0, 1 to the K. So I pick generators, P generators, large polynomial generators. I feed G of S1, G of S2, up to G of SP to the distinguisher. And I say, what is the probability that the output is 1? Okay. Minus, well, the other experiment is I pick numbers U1 up to U sub P randomly from 0, 1 to the 2K, and I feed the distinguisher with U1, U2 up to UP. And what is the probability that the output is 1? Okay, I claim that the difference between these two experiments is negligible. Does that make sense what I'm saying? I'm saying the pseudo-random experiment, the pseudo-randomness experiment, is either I give the distinguisher G of S for a random S, or I give him a uniformly random string, and he couldn't distinguish. Yes?
Does the distinguisher have access to the definition of G?
Yes, absolutely. This is always going to be the case. The distinguisher, the adversary, has access to the definition of any algorithm. The only thing they don't know is a secret or a key. Good. Right? So the only difference between this and really the pseudo-random game is I'm actually giving him P pseudo-random strings or P uniformly random strings. Right? One of the two. And he should be able to distinguish. That's the point. Why is this true? Two words. Again, what you have indistinguishability between an apple and an orange. Okay, you want to say that P apples versus P oranges are indistinguishable. How do you do that sort of thing? You reduce it to indistinguishability between one apple and one orange, more or less. Okay. Any thoughts? How do you? So from the definition of a pseudo-random generator, you can prove it. Very easy. Very easy. You just do this like 20 times, and then it will be very easy.
So it's a hybrid?
That's it. Yeah, that's it. Very simple. The zeroth hybrid is when all the strings are pseudo-random. The P plus 1 the P hybrid is when all the strings are random. The I hybrid is the first I guys are pseudo-random, the other guys are random. Okay? So if you can distinguish between the top and the bottom by contradiction, you can distinguish between some I hybrid and I plus 1 hybrids, which is basically means you're distinguishing with one copy. And here it's very important that the distinguisher knows the definition of the pseudo-random generator. if you work through the hybrid argument, that will actually become important. Okay, so this is true, and this is easy to prove. Okay, now let's actually get into the proof of the GGM construction. And hey, guess what? There are two words that describe the proof. Hybrid argument. Okay. Hybrid argument. Hybrid argument. Which means I have to define the hybrids first. So my zeroth hybrid. My zeroth hybrid is the following. I wanna these the bad letter. Hybrid zero. My zeroth hybrid is the following. You know, in all these hybrids, I'm going to run the distinguisher, and I'm going to give him access to a function chosen from a family of functions. Okay, some family of functions. In D0, that family is the uniformly random family, I believe, or the other way around. No. It's in D0, in H0, sorry, the family of functions I give him is the pseudo-random family. What does that mean exactly? Let's think of this as a as an interactive game. Okay, between there is the distinguisher sitting here, right? And he wants oracle access to a function. He says, "Give me oracle access." Okay, what does that mean? He keeps asking questions. He expects the function evaluated, the same function evaluated on all these things. Okay. Now I'm going to play the game. And I'm going to play the game how? Well, here it says I play the game using a random function chosen from that family. That's what I'm supposed to do. Here it says play the game with a totally random function from n bits to n bits. And the guarantee, right, contrapositive, right, if he could break this pseudo-random function, he distinguishes between these two possibilities. Okay? Contrapositive. If this were not a pseudo-random function, the distinguisher tells these two apart. So hybrid zero, again, getting back, is where I pick a function from Fn. In other words, yes, it's a caricature. What does this mean, this picture? It means, imagine for a moment that I picked a random S. Yes, this is me, not an adversary, clearly. I picked a random S. I drew this tree. Okay, I drew this whole tree. And when he asks me for X, I give him GX plus. That's what I'm supposed to do. Yes? Now you say, well, you are polynomial time. You told me that you're polynomial time. How are you going to draw this whole tree? Yeah, I can't. The beauty is that I can do this as I go along. Right? I don't have to draw the whole tree. I can recreate it just in time. Whenever he asks me a question, I go down this path. So I can do this. I can actually give him this. And hybrid, what's it, n? Is it? Is where well, actually, you know what? Let me go one step at a time, okay? Hybrid 1. What do I do? Here is what I'm going to do. I'm going to look at the first level of the tree, okay? I'm going to say, this is, before, it was actually the first and the second half of a pseudo-random generator, right? Now I'm going to make it into two truly uniform strings, uniformly random strings. And then the rest of the tree, well, it's the rest of the tree. G0 of S0, G1 of S0, G0 of S1, E1 plus 1. The point is, I cut off the first layer of the tree. There's no root anymore. And I replace these two guys by truly random numbers. That's the rest. The rest of the tree is exactly the same as before. Why? Because you go down this path, you compute the pseudo-random generator, and you do the right thing. Okay, you do it as before. The only change is that the first level is truly random numbers, not pseudo-random numbers. That's first hybrid. What is the second hybrid? What do you think?
You then cut off the S0, S1 layer.
Cut the guy off, right? This guy off. So this I'm going to denote it by. Then I'm going to say, here is 4 numbers. Which way is it? 1, 0, 1. Okay, these guys don't exist. I start at level 2 with fresh 4 random numbers. And then I define the tree exactly the same way as before. Okay. That's hybrid 2. What is hybrid 3? You know where it's going. Right? And hybrid n is what? If you keep doing this, what are you going to get at the end? Random numbers. I keep cutting off the tree and replacing each level by truly random sequence of numbers. At the end, I'm going to get, well, there's no space, but whatever. S0, 0, S 0, 0, 0, 0, 0, 1. You know what I mean. These are truly random numbers. Okay, so the point is that each of these hybrids defines a class of functions. Right? Here it's a class of all functions. Here it's a class of pseudo-random functions. In the middle, it's something. Okay? Right? Here's how we do. The adversary says if I give him a random function, if I give him oracle access to a random function chosen so, minus he outputs 1 with significantly different probability than if I give him a function chosen so, in other words, a random function. Therefore, hybrid argument tells you that there is an I such that if I give the adversary oracle access to a random function chosen from hybrid I, he outputs 1 with probability significantly different from if I gave him a random function chosen from the next. Good? Okay. This is the essence of the hybrid argument. So what? Okay, so what? Okay, so let's say for a moment, between the two of us, you and me, he distinguishes between hybrid 0 and hybrid 1. Okay, it's a simple thing. He doesn't have to. He could say 500 and 501, but let's say for a moment. In other words, the probability chose a function f from hybrid 0, distinguisher f is 1, where is that space? Minus the probability that you chose f from h1, distinguisher f is 1, is bigger than some, if the original thing was epsilon, this is going to be bigger than the original, so between 0 and 1, if I distinguished with difference epsilon, what would this be? Triangle inequality would give you 2 to the n, say it again, over n. Right? It's triangle inequality. Which is good enough, right? Epsilon is 1 over polynomial, epsilon over n is also 1 over polynomial. Okay, so this I know. And I want to use this guarantee to break this pseudo-random generator. Okay? To distinguish between an output of the pseudo-random generator and a truly random string. So in other words, I am playing this game, yes? So this is the PRF adversary. I am the D prime, which is the PRG adversary. Okay. I'm going to use this guy to break the PRG. This guy is a subroutine to me. Okay, so I'm going to use this guy, run this guy. So what do I get? I get either G of S or, which is pair of strings, or I get random pair of strings. Yes, and my goal is I'm supposed to say which one it is correctly. So what do I do? When I get this pair of strings, I'm going to say this adversary is going to tell me some useful information if I fed him this versus this. Okay? I guarantee 1 over epsilon, epsilon over n. So I want to play one of these two games. But of course, if I knew which game I'm playing, then that's not very useful. Yeah. What do I do? So I get this pair of numbers. Yeah. I want to play with the adversary, and I guarantee I'm going to play in either this game or this game. What do I do? There isn't much of a choice. These guys are they're more or less the same, except a tiny bit of place where they're different. Yeah. So I say the following. I take my y1, y2, I put it in the second level of the tree. Namely, I put it here. Maybe 0 and 1, 1 and 2. Sometimes I'm a mathematician, sometimes computer scientist. Yeah, I'm supposed to. So I get y0 and y1, I put them here. I put y0 here, I put y1 here. Now let's try to think. If y0 and y1 were the output of a pseudorandom generator, then which game am I playing here? I'm playing the left game, yes? Because I put y0 here and I put y1 here. I didn't know that there exists a seed that generated y0 and y1. Okay, I am playing in this game. If y0 and y1 together were truly random strings, then clearly I'm playing in this game. I don't know. Obviously, I don't know, right? I don't know which game I'm playing, but it's one of the two. And now I play with the adversary. What does it mean, play with the adversary? He asks me questions. He says, go down to the xth leaf, give me the answer, which I can compute in both cases. Yes? I can I can start from here and compute it. It'll be either a leaf in this game or in this game. I wouldn't know again. Right? And eventually he says, I'm going to distinguish, right? Then of course, he's going to distinguish. Of course I'm going to distinguish. Does that make sense? What I'm saying? So far, so good. Very good. So that is for the 0. That is if we distinguish between 0 and 1. Right? What if we distinguish between 20th hybrid and the 21st hybrid? I want to do the same thing, really. Right? I want to get a pair of strings, y0 and y1 this way. Well, actually, it's not going to be a pair of strings. It's going to be many pairs of strings. And they're either all outputs of a pseudo-random generator, or they're all truly random. I'm going to plop things into the, I guess, ith level. In one case, it will be the I-1 game. In the other case, it will be 1. Yeah. That's exactly right. Because, to fill the ith level, I need many pairs of outputs of either random or pseudo-random. That's where I use that lemma. It doesn't matter if I get one output of pseudo-random generator versus random, or if I get polynomially many outputs of the generator versus random. Doesn't matter. The important thing to note here is that as I go down the tree, let's say I am in the n over 2th hybrid versus n over 2 plus 1 hybrid. I am supposed to feed the other, I'm supposed to give the interface to the adversary, which is either totally random in the ith level, or totally random in start from the ith level or start from the I plus 1 level. I cannot construct this entire function. I just cannot. I mean, I don't have the time. Till the n over 2 time, I don't have it. But guess what? I don't have to. All I have to do is construct this tree as and when the adversary asks me questions. That's all I need to do. It's very, very important, right? And I can do it. Takes a little bit of thought, takes a little bit of bookkeeping. Yes? So maybe let's do it. We have 8 minutes. Why not? Right, so some ith level, right? So now there's 2 to the I nodes here. Versus I want to play in the, so either start from the, this is hybrid I plus 1, I believe, and this is hybrid I. Yeah? I want to start from the ith level or the I plus 1 level. So, or initially I do nothing. Okay. I run the adversary. He asks me for a question. Right? He asks me, give me some leaf of the tree. And I say, well, the way I'm going to do it, so let's say this is the leaf he wants, right? I'm going to say, look, what do I have? I have many pairs of numbers, right? Y10, Y11, Y20, Y21, YP0, YP1. So each of these is either the output of pseudo-random generator or totally random 2k-bit number, right? 2k-bit string. So if he asks me for this, what am I going to do? I am going to take the first number in the pair, right? And I'm going to give him Y10. Why do I do it? Because if this were truly random, then I'm clearly playing in this game, right? This whole thing is supposed to be random. I can generate it as and when. But if this is an output of a pseudo-random generator, then I know that Y10 is the left child of this tree, so I'm actually, so this is as if I took the seed S1, right, and expanded it to Y10 and Y11, and I gave you Y10. That's what I'm supposed to do, but I'm doing it without actually knowing what I'm doing. And now the adversary says, well, here is another pattern. What do? I pick the next pair of numbers, right? And let's say this is actually the right child. So then I give him Y21, okay? Because he's going to ask me for the left child later. Now he comes back and says, well, you know what? I asked you for the left child. Give me the right child now. Something. Okay. What do? I know that these two guys have to be consistent, right? So I better feed him Y11 here. Right? Which makes sure that if Y10, Y11 was the output of a pseudo-random generator, this is exactly the game that I'm supposed to play in the ith hybrid. If they were random, well, then it doesn't matter. I mean, yeah, so you have to be careful, very careful. You do the bookkeeping to keep track of which queries you answered how. But that's okay, because he's going to only ask me a polynomial number of queries. I can keep a polynomial size table describing what I did. That's how. Be a bit careful what that. Okay, so that's pseudo-random functions. Good. So this actually gives you a solution to the symmetric key encryption problem, which I unfortunately erased, but will let me write down a symmetric encryption scheme, a secret key encryption scheme. Here is a secret key encryption scheme. It's exactly what we wrote down before. Gen samples a random seed of k bits. This is the secret key. Right? What do I do to encrypt a message M with the secret key S? So let's say the message M is, I don't know, k bits. If it's bigger, chop it into blocks and do independently encrypt these guys. What do? I pick a random R from 0, 1 to the end. So R is essentially the leaf, a random leaf in the tree. Right? So compute fs of R, right? The label of the rth leaf, XOR with the message. This is the ciphertext. That's it. Is it the ciphertext?
You also should include R.
Okay. Yes, so you need to know where to look. The decryptor needs to know where to look. So decryptor S and C, you look at this, parse it into a pair, apply FS on this, which I can do because I know the secret key, XOR with this guy, I get this. That's it. No state, absolutely no state. But there is one thing that we introduced here, which wasn't there before, in our very first attempt. Our very first attempt was deterministic, if you think about it. I didn't have any extra randomness. I get the secret key, the message, done. This is randomized. That's not necessarily so. Okay, so this is what it is. This pseudo-random function business has a million different applications. This is not the only construction of pseudo-random functions. You can get more efficient constructions. What do I mean by that? So here, to compute a function on a leaf, on an n-bit string, I need to apply the pseudo-random generator how many times? N times. And it's not even parallelizable. Okay, I need to apply a pseudo-random generator on the output of the it's very sequential computation. Turns out none of these things is really inherent up to a limit. You can get very parallel constructions of pseudo-random functions, but that you need to assume, you need to make concrete computational assumptions, like the Diffie-Hellman assumption or the discrete log assumption. These give you very nice constructions of pseudo-random functions. These guys have tons of applications. Learning theory is one thing that I'll mention very, very quickly. So what does learning theory say in 1 minute? Okay, so I have a class of functions, yes, and I get to query these functions. I get to say, well, here's a picture. You know, tell me if it's a cat picture or a dog picture. Okay, that's the kind of, there's a ground truth function F that takes pictures to labels, and I get to query this function. Okay? And I'm supposed to learn what this function is. In other words, I'm supposed to output a function that agrees with this guy. Quite well. This is a class of functions that is unlearnable. By definition, the security of pseudo-random functions says, if I query the function, you can do it polynomially many times, I won't even be able to distinguish between a new output, the output of the function on a new input, versus totally random. I won't be able. It looks like, this function looks like truly random function, so I can't learn this family of functions. And this is inherent, right? If you think about machine learning and cryptography, they're like matter and antimatter, right? Cryptography says, I'm going to make things up so that you cannot learn. Machine learning says, I'm going to try to learn. Okay, so of course they are and really, truly amazing things happen when matter and antimatter come together. Okay, so when you want to make sure that people can learn certain things but not other things, amazing things happen. That's one thing. The other thing is very surprising application of pseudo-random functions. So to prove it to complexity theory. Complexity theory, what do? You try to prove P naught equals NP. Doesn't work, but you keep trying. And then people sort of came up with various proof techniques over the course of time. During the period of optimism in the 1980s, right? People thought, by the 95, I'm done. I'm good to go, right? And it turns out that all these proofs have a certain structure, and we call it natural proofs. We'll post the links on the Stellar page for those of you curious. No, there's a general class of proof techniques which encompasses quite a lot of what happened pre, I suppose, 2000s, right? Josh, sort of, yeah. And very surprisingly, you can show that if you can compute pseudo-random functions in a certain class, here clearly polynomial time, right? Polynomial time function. Then you cannot, these natural proof techniques cannot prove a circuit lower bound against this class. In other words, really what I want to prove is I want to come up with a function or a language, right? And I want to say this guy cannot be computed in polynomial time. That's P not equals NP. Well, actually, this function is nice enough. It's P not equals NP. Yeah, that's what it is. So if there are pseudo-random functions in P, then all the stuff that people did in the first 20 years, 30 years of complexity theory, called natural proofs, cannot prove such a low bound. So you have to do something else to. It's a very surprising application to complexity theory, but Osborne and Rodish, they got the Gödel prize, right? Yeah. Very nice applications. This is just the beginning of kind of the things you can do with pseudo-random functions. In fact, in the problem set, you will do two very cool things. So by the way, there is a sign-up sheet here, the sign-in sheet here. Make sure you put your name in.